Hey Eva,
Hi,
how are you?
I'm good. How are you?
I'm doing fine. Uh, so for these office hours, how these go are like I just answer like any like questions. It's like the AT3 drop-in. I don't have anything prepared. I just like show up.
Oh, okay. I was wondering if we could go over some of the reactions that the prof from last class that he went over.
Oh yeah. Let's see. Let's go over that right now.
Okay.
Let's see. Let me pull up the notes. Okay. Okay, so first let's go over like how to make alkenes, like to prepare alkenes. There are two ways that we could do that. Primarily E2 or alcohol dehydration. And here are the reactants that you will see if you have an E2 reaction or an alcohol dehydration. So for E2, you're going to have a good leaving group, which your good leaving groups could be any halogen like chlorine, bromine, iodine. It could also be uh, OTS, OMS, like those random letters,
Mhm.
OTF as well. And these could be mostly secondary, tertiary substrates, and strong base, strong nucleophiles. So think of atoms like oxygen or nitrogens with negative charges. If you see an oxygen or nitrogen with a negative charge, that is a strong base and a strong nucleophile,
Okay.
right? And there are going to be two types of these. There's going to be unhindered, which is basically all of it. And there are only two types of hindered strong bases that you need to know. Tert butoxide, which Pascal writes as this, and it looks like this oxygen negative charge with the tert butyl group or like chicken leg kind of thing. This is very bulky. Another thing that you could see is LDA, right? Where that LDA is going to be also bulky because we have a negative charge on this nitrogen, which shows that it's a strong base, strong nucleophile. But these two isopropyl groups here are bulky groups, which is why we consider them to be bulky or hindered. Some unhindered ones, some examples of that would be something like ethoxide, hydroxide ion. Um, the chain of the ethoxide does not matter. It could be like really long like that because it will um like basically float away or from the reaction, right? But once you have something like this on the alpha carbon, then this will be considered hindered. But if you just only have one R group on the alpha carbon, then this is considered unhindered, right? And do you remember which one gives you the Zaitsev product and which one gives you the Hoffman product?
Um, would it be unhindered gives you Zaitsev?
Yeah, that's right. Unhindered would give you Zaitsev, and Hoffman, I mean, hindered would give you Hoffman, right? Where Zaitsev, you could think of it as like the more stable double bond. Hoffman will give you the less stable double bond. Okay. Also for E2, do you remember the transition state name that it goes through?
Um, like, uh, Is it like anti-peri? I have no idea.
Yeah, you got it. Anti-paraplanar transition state. Huh? And do you know what that means? Anti-paraplanar, or you just memorized it? Yeah.
I remembered it, but then well, it doesn't it mean like something about like the position of never mind, I forgot.
So the position of the beta hydrogen, well, Lewis calls it the alpha hydrogen, but I think normally it's called beta hydrogen, is opposite to the leaving group. So an example of that would be something like this. Let's say this hydrogen leaving group, or let's make it more clear. Let's say we have like this and good leaving group bromine here. And let's say we put that under small strong base NaOH water. This is our good leaving group right there, the bromine. The substrate is secondary because this carbon here is attached to two other carbons. And consider this carbon here holding the leaving group the alpha carbon. The other carbons are going to be the beta carbons, which is why we are only considering the the beta hydrogens, right? So let's draw out all of the beta hydrogens. That's one beta hydrogen, and here are the other three beta hydrogens on this carbon. We are going to be only concerned about the beta hydrogens that are opposite side to the leaving group, which is going to be either this dash hydrogen or that dash hydrogen, because those are opposite to this wedged bromine there. Right? Which dash hydrogen do you think we are going to take to form the more stable double bond, given the unhindered base?
The one on the left.
Yeah, that's right. That's right. Because that will give us the more substituted double bond. And the more substituted the double bond is, the more stable it is due to hyperconjugation. Right? And notice how this wedged isopropyl group got converted to a planar bond. And do you know the reason why that happens?
Um, no.
So the reason why is because this carbon right here was an sp3 carbon with 4 bonds, but we converted it into an sp2 carbon because it has a double bond now.
Okay.
And sp2 atoms are flat and planar, which is why there's no wedges and dashes on the carbon that is double bonded.
Oh, okay.
Mhm. There are like a lot of different cases for these E2 reactions. Remember back in 118A, there were like a lot of cases where the hydrogen is not anti-periplanar, so you have to rotate it if it was linear, or if it was in a ring, you can't do any rotation, so you're like forced or locked into like the other position. So there's a lot of cases that E2 can happen. You want to do practice problems on that, or move on to the alcohol dehydration?
So I mean, it's basically like what we did like last quarter, right? But
Uh-huh.
so we're just gonna be focusing on E2 then for this.
E2, if you're given a good leaving group on the secondary or tertiary substrate with a strong base, strong acid. Strong base, strong nucleophile. That is
Okay.
either unhindered or hindered. That's the sign of E2. You can also have alcohol dehydration, where for alcohol dehydration, what you'll see as the reactant is an alcohol, most likely secondary or tertiary alcohol. If it's primary, then that will most likely undergo a SN2 reaction, which will form the symmetrical ether. But we don't want that. We want an alkene. So secondary or tertiary alcohol under a strong acid like H2SO4 and heat. Pascal, I think he says like high heat is like around 170 to 180 degrees Celsius. And um yeah, that's basically it. Alcohol dehydration is much easier to recognize. You just have secondary, tertiary alcohol, and then the acid and heat. Let's go over an example of that. Let's say we have. Oh, and also a tricky thing is that this goes through an E1 like mechanism.
Okay.
And what is that extra step that a lot of people tend to forget for SN1 and E1 mechanisms?
The carbocation formation.
Yeah, well, the carbocation formation is always the first step. That's correct. And whenever you form that carbocation, what do you always have to look out for? That's the step after the formation step
Oh,
that
like
people forget
the
about.
hydride shift or methyl shift?
Yeah, hydride or methyl shift. That's right, hydride or methyl shift. And the new thing this quarter that we didn't go over in 118A is something called let me move this somewhere else. A ring expansion.
Oh, okay.
And what is this? Oh.
Oh, is that what we kind of went over like last like the last tutoring session with like anytime you see like a ring, you want to try to get it to like a bigger ring.
Yeah, yeah, like a bigger, more stable ring. Or let's say ring expansion. Yeah, that's right. That's right. Uh-huh. Where we didn't go over an example of that for 118A, but there could be an example of that for 118B.
Okay.
So before we do that, let's do a regular example of let me just do three examples. Let's say, oh, are you on an iPad or tablet?
Yeah.
Uh, is you connected to Zoom or is it are you connected to Zoom on a laptop?
Yeah,
Or
on my laptop. Yeah.
oh, I see, I see. Do you want to try connecting your iPad to the Zoom so you could try like writing this mechanism out for extra practice?
Yeah,
Mhm.
sure. Uh, I think it's here we go. And I say no audio and then yeah.
Yeah, no audio, right?
Okay. I'm used to having like a note card for like the E1 and SN1, all that
Oh,
mechanism.
like
So
with the tables and charts.
yeah.
Oh, shoot.
Yeah. Um,
Mhm. So instead of having a note card and memorizing the reactions, let's
mhm.
try to logically think through like these reactions and what's going on. So what is an H2SO4? Is that a nucleophile, electrophile, acid, base,
It's an
reducing
acid.
agent? Acid, right. And if we have an acid, we have to look for most basic atom. So what do you think is gonna happen first? If we have a strong acid.
So it's like protonation.
Yeah, yeah, that's right. So let's protonate the most basic atom, which is going to be
So oh, do you want me to draw it or okay.
yeah, uh-huh.
Well, the O attacks the H and then doesn't this like go like that so then it breaks apart and becomes like a negative.
Yeah, it becomes a negative HSO4 minus.
Yeah.
Mhm.
So then it's like and then negative HSO4.
That's right.
Um
And what charge would this oxygen have here with three bonds?
would it be positive?
Yeah, positive charge, right. And what you did there was that you converted this bad leaving group OH into a good leaving group OH2 plus,
Right.
right?
So then that pops out, right?
Yeah, just leaves by itself, like an E1 mechanism.
And then you just have a positive charge here? Or-
That's right, because that carbon there lost the bond.
And then how do you tell if it's like an E2 reaction then from, or I mean, or an E1 reaction from?
So E1 reactions will always have competition with SN1, and SN1 is usually always major unless you have high heat. If you have high heat, then the E1 product will be major.
Okay.
Yeah. So if you see a heat symbol or if you see 170 degrees Celsius to 180 degrees Celsius, then you're going to favor the E1 product.
And is it like every time you have acid, it's normally like elimination reaction, or am I just
So elimination reactions, it's usually under basic conditions, like you know how in the E2 examples we did, we use strong bases to deprotonate the beta hydrogen to make the double bond.
Mhm.
And in this case, this acid here is doing dehydration with alcohol. So it depends on what your substrate is too. Like in the previous cases for E2, our substrate was a good leaving group. They had good leaving groups like bromine, iodine. If you have an alcohol substrate, right, under acid, then this is an alcohol dehydration reaction. Right. So
Okay.
there's different factors to look out for. The reactant molecule that you have, does it have an alcohol or a good leaving group? And also your reagent. Is it an acid or a base? If you have an alcohol combined with a acid, then this is an alcohol dehydration mechanism or an E1-like mechanism. If you had a good leaving group and a strong base, then that's going to be an E2 mechanism with a strong base and good nucleophile. But here we don't have a strong leaving group. We have a bad leaving group, OH, alcohol, and an acid, which is basically an opposite of E2. So this is a sign of an alcohol dehydration reaction, right?
And then
Mhm.
it attacks the Earth. Oh my God, my pencil is not.
Yeah, the Zoom whiteboard is kind of glitchy.
Is that you erasing it or is that me? I don't know.
Oh, oh, I think it's you.
It's me? Oh
Yeah,
my
yeah.
God, it is
Uh,
not working.
are you on the eraser tool?
Oh.
Yeah. Hey, you can go back, like the undo button.
Yeah, let me just okay.
Yeah.
Anyways, okay.
Mhm.
All right. Okay. So it's like that, and then there's a hydrogen here,
Yeah.
uh, and then the negative HO4 but attacks that, and then that goes like that. And then
Okay, let me change this problem up a little bit because you will get the great product, which is that. But the mechanism, there's one thing that's missing in the mechanism. But you got lucky because like this reactant
oh,
here it gives you the correct product if you don't do the extra step. But let's say we had something like this. Then our product would not be that. This would be the minor product,
okay.
right?
So if we had like uh, so from here, you're saying
Yeah. There's one more step before the elimination step.
it'd be like the carbocation, the
Rearrangement step.
arrangement.
Yeah. That's the step that a lot of people forget about.
Isn't it you kind of swap places with the hydrogen, right? So this goes here.
Uh-huh. Yeah, you swap places with the hydrogen, but it's not the positive charge that's moving, it's the hydrogen that's moving there.
Oh, okay.
Uh-huh. Positive charges never move, it's electrons or bonds that always move.
So do we need to draw out that the step for carbo cation moving, or because normally I could just like see it and then just
Mhm.
put it here.
If he asks you to draw the mechanism, yes, you have to draw out the hydrogen specifically and draw out the hydrogen moving there um to show
Point.
that that hydrogen is now here and the positive charge is now there.
Oh, okay, okay,
Yeah. Mhm.
okay. And then um And then you could do this hydrogen too. So it would give you like
Nice.
should I draw out both products or just the one?
That is good. That the major products here
Yeah.
is good.
Okay.
Uh-huh. Right. Where our acid catalyst gets reformed, but I don't think you need to write that in the answer box because that's not organic. Mhm. So that's good. That's good. Let me screenshot this so I can put it in the notes. And okay, now let's do one more, two more of these, where they're gonna be different slightly. Let's say, mm, oh yeah. Mhm. Try predicting the product for this reaction and draw the mechanism as well.
Okay.
Let me pull up a practice problem for the next thing that's coming up.
Oh wait. I'm kind of confused on this one because I thought you could do
Mm.
like the carbocation shift, but
Hmm.
there's no hydrogen on the other carbon, so
Hmm.
I use
Yes. So we don't want to do a hydrate shift here because that would make a less stable carbocation. So that's no good. There is one more shift besides a hydrate shift that you could do to make a more stable carbocation, and that's called a methyl shift.
uh,
Since this carbon here does not have wait, how do I change the color of this over here? Since this carbon here does not have a hydrogen, but it does have a methyl group, you're gonna
yeah.
move one of the methyl groups there,
Oh,
and
I thought you could do that. Okay.
yeah, this is the cursed thing that people say it looks really weird, right? Where that red circled methyl group just migrates onto that carbon right there, and the carbocation swaps places with that methyl group like that.
Okay, that makes sense.
I think this is gonna probably show up on the exam because this example was shown in lecture too, like the methyl shift example.
Yeah, you're probably right. I completely forgot about methyl shift. That's
Yeah.
important. Okay, that
Mhm.
makes sense. Oh my God. No, that doesn't make sense. Is that correct then? Like this one, this product here?
Yeah, that's correct.
Okay.
That's right. Where there are three different potential beta hydrogens you could grab. You drew out the correct one. The other two are these right here, but you drew out the one that is going to give you the more stable double bond. That's right. Okay. Now let's do one more example of this alcohol dehydration. Let's see. Why is it? All right, let's do this one. Oh, hmm, okay, try that one.
Okay. So I want to do the carbocation. Is it more stable on on the ring structure or
So this carbocation right here is a secondary carbocation because that carbon is bonded to two other carbons,
yeah,
but this carbocation here is tertiary because that carbon there is bonded to three other carbons.
yeah, okay.
I see. So this is the new tricky concept here. Um, you did a methyl shift, which is usually good, but if we see a carbocation right next to a ring that can be more stable
Yeah,
by like expanding it by one carbon,
yeah.
then we have to do something called ring expansion.
Oh, so you don't move the carbocation then if you want to do ring expansion?
The carbocation will still be moved because instead of moving that methyl group, you're going to move a different bond. What
Oh,
bond are you going to move instead?
um, well, you want to break open the bond. Um, so is this where you like number it and then you move
Mhm.
like first.
Yeah, this is where you number it and you choose the bond that would make the ring bigger by one carbon.
Okay. Yeah. I'm a little confused on this part.
Mhm. Yeah.
So I guess
So, mhm.
this would be like one,
Yeah, yeah, yeah.
3, 4. So then this would open up. So one would open up technically, right? And then
The bond between one and
1 and 2.
1 and 2, yes, yes, that's the bond. That's the bond that's gonna move. You got it, right. And where is that bond gonna go to?
So it's technically gonna like open up here.
Mhm.
So then, is it only
Oh,
it like
right, right. It won't do it from here. Start from here, right?
okay.
Instead of doing the methyl shift, we're gonna do this ring expansion thing.
Oh, okay. Okay.
Mhm. So let's erase everything underneath. Yeah.
Okay.
Mhm.
So I'll just erase this part.
Yeah.
And then I'll start from the first this part, right? You were talking about this one, right? This one, right? That
Oh, starting from this one with the carbocation that I pointed in purple.
Oh,
Uh-huh.
okay.
Yeah.
Okay.
And the bond between you said 1 and 2 is the one that's gonna move.
Mhm.
And where is that going to move to? Which carbon is missing a bond right now? Which carbon wants it to gain electrons?
Isn't 2 then gonna be losing a bond or
Uh-huh. Yeah, yeah. 2 is gonna lose a bond. And which bond is gonna gain a bond? Which bond right now do you think is electron hungry?
1 is gonna gain a bond?
Don't think of the ring. Think of the other carbons outside the ring. Which carbon looks very um electron poor?
The carbocation on
Yeah, the carbocation. So this bond here is going to make a bond between one and that carbocation right there.
okay.
Right. So the better way to number this is this 1, 2, 3, 4, and then this carbon with the carbocation, the extra carbon. So if we start with a four-membered ring, that carbocation is gonna be carbon number 5.
Like that, and then um so you labeled it 1, okay.
Where that circled green bond is the bond that moved between 1 and 5.
Okay.
Yeah, and then carbon 4 has that methyl group still, which that methyl group that you just drew right here is that methyl group right there.
And then would 1 take that methyl group on the end then if it
So let's see. Oh, we which carbon lost the bond? Looking at the green numbering system, which carbon lost the bond?
um 4.
Yeah, 4. So that's why 4 will have the positive charge. And also, you know how that carbon 5 there also has a methyl group?
Yeah.
Let's draw that in as well. Now this is where you continue with the E1 mechanism.
Oh, so the methyl goes to 5 then, like the one next to
The
it.
yeah, the group which the methyl group, which methyl group are you talking about?
This one right here, like on the end, like right there.
Yeah, yeah, yeah. That one is still on 5 because when I numbered at 5, that methyl group is still attached to 5.
Oh, right, you renumbered it. Okay, okay.
Uh-huh. Right, right. The
That,
green 5 is still attached to that methyl group there.
okay, that makes sense.
Mhm. And then continue and finish the mechanism.
So then the carbocation goes here, and then, or no, it can
Oh,
just stay there.
yeah, it could just stay there. And if we wanted to move there, that carbocation is not gonna move. It's gonna stay there. The thing that moves is gonna be a hydrogen or a methyl.
So wait, why can't the carbocation?
Yeah, the carbocation can't move because think of the positive charge as a sign of missing electrons. There's nothing there to move. Only bonds can move. So
Uh,
like, let's say we have something like this carbocation there. That positive charge can't move there because there's nothing there. What does happen is this hydride shift here. That hydrogen does move there to have this hydrogen here, where this carbon here lost the bond, which is why it has a positive charge.
Right.
Meaning that there's missing electrons there. You can't move like empty space. There's nothing to move there.
Okay, so you're just saying just to make sure to show like the hydride shift during like if you wanted to move it, like
Yeah, the hydride or methyl shift.
okay, got it.
Mhm.
Um,
Yeah, nice. That's the final answer.
okay,
Here,
that makes more sense.
here.
I think it helps to label the carbon that you're gonna connect it to, because then I think I forgot to do that.
Like the new one, right? Like the
Yeah,
new bond.
yeah.
Yeah, that's good. That's good. Let's do two more problems related to this here. Just to reinforce the mechanism of what you just learned. Okay. So let's say yeah. Try these two practice problems.
Okay. I'm gonna do it in a different color so it's better.
Mhm. Mhm. Did you accidentally erase what you had?
Yes.
Oh no.
I keep doing that. It's okay.
Oh, nice. Yeah. And then, which carbon that you numbered lost the bond?
Um, the three?
Yeah. Uh-huh. Which is why that three is going to have the positive charge. And the way I made this problem is kind of bad. Let me just erase um this methyl group right here. So yeah, erase that methyl group that I just erased on the other ones. So then we have a clear cut answer. Because the way I gave it, there's a mixture of products, which is going to be hard to grade because you got multiple products. And this one. Yeah. Okay. And now, yeah, we continue and finish the mechanism. Oh wait. Did you just like move on to the next problem?
Yeah, wait, oh,
What happened here?
right. Oh, right, I forgot. Right. Oh, okay. So, hydride shift then?
Yep, hydride shift. Nice. Mm-hmm. And then one last step for that.
Okay.
Oh, okay. So let's see. There is one more um beta hydrogen that can give you a more substituted double bond. Right now you have one, two, three tri-substituted double bond.
Yeah.
There's another beta hydrogen from that carbocation that can give you a tetra substituted double bond.
Like, smaller ones.
Mhm.
Sorry.
No, no, it's okay.
Henry, Henry, table. Okay, anyways.
Mhm.
Okay. So you mean on the other carbons, like the beta carbons?
Yeah. So this is one beta carbon. That's the other beta carbon. That's the other beta carbon. Let's
Okay.
draw out the hydrogens. There is another beta hydrogen besides the one that you grabbed that can form a more stable double bond.
Oh, so it's this one then, because it's
Yeah. Uh-huh.
three instead of two.
Yeah. Uh-huh. That's right.
I'll just draw it over here and then erase that. And that looks really sloppy. Oops. Like there. Okay, there you
Oh, so
go. Wait.
uh-huh. When we grab this hydrogen here, where is the double bond being formed? Where's the carbocation at?
Uh, oh yeah, it's here. Then the double bond would be.
Yeah, yeah, there you go. Double bond is there, and yeah, there we go. Then now here we have a one, two, three, four tetra substituted double bond, which is more stable, more major than
Okay.
the tri substituted one.
Okay.
Mhm. That's good. That's good. Okay.
So should I do the next one or?
Let's move on to the hydrogenation
Okay.
reaction, the alkene reaction. Okay. So the stability for alkenes goes like this. The least stable one is the unsubstituted one where there's no R groups at all. Then the monosubstituted one. Then we're gonna have three different types of di-substituted ones. We could have cis, which is gonna be the same as same stability as a geminal, but both of these are less stable than a trans, right? All three of these are di-substituted. Substituted because all of them have two R groups. This is cis, this is geminal, and this is trans. Okay, and then they are less stable than the tri, and then that tri is less stable than the tetra. Okay, so stability increases from left to right in this case. If that's the case, which one of these has the most amount of energy?
Um, so like, wouldn't it be like the less stable then would have more energy? Or
Yeah.
yeah,
Huh?
so it would just be the the one on the left.
Yeah, the
Just the-
substi substituted one. Yeah. Okay. So this could be a question where, let's say, I also the double bonds, there's also different things as well. Like let's say we have a conjugation versus isolation, right?
Mhm.
Uh, which one is more stable?
Um, huh.
Which one do you think can do resonance?
Um, is it the one on the left then?
Yeah, yeah. The one on the left, because do you remember how resonance is like a network of sp2 atoms,
Yeah.
adjacent sp2 atoms? That's a network of that where we could like move that double bond there and that double bond there to get this um resonance structure right here. But these are sp3 roadblocks, which blocks resonance, no resonance. Right? If that's the case, which one will have higher energy?
The one with resonance.
Uh-huh.
So,
Yeah, so the one with resonance, is it more or less stable?
oh, it's more stable.
Uh-huh. More
So
stable, which means it has.
less energy.
Yeah, so that could be tricky, right?
Huh. Okay. Yeah.
This has higher energy. I feel like this is gonna be a tricky concept on the exam, like the energy thing. Uh-huh. And the way that he's gonna ask it is, let's say, which of these is going to give off the highest? And he might not say energy. He
Mhm.
might show the symbol right here.
Delta H.
Heat of hydrogenation.
Heat of hydrogenation.
Yep. Which is a form of energy.
Hmm.
And that form of energy goes through after the hydrogenation reaction, which is H2 and some kind of catalyst like PDC from hydrogenation reaction. So for example, some kind of alkene like that goes through H2 and some kind of catalyst like PDC. All that does is that it gets rid of that double bond and adds two hydrogens. One, two. Because before the double bonded carbons already had one hydrogen, which are the purple hydrogens here.
Hmm.
We added these extra hydrogens from the H2 right there,
Okay.
right? And the less stable the double bond is that goes through this reaction, the more energy it has, which is why the more heat of hydrogenation it will give off.
Okay. So the less stable usually you want if you want more energy.
Yeah, yeah, less stable, more energy.
Okay.
So, so now let's go over more examples of these where you have to rank them from lowest energy to highest energy now.
Okay.
Okay. So let's say okay. Rank the following from lowest energy to highest energy, where let's say the lowest energy is gonna be 4 and highest energy is gonna be 1. Lowest energy 4 to highest energy 1.
Mm.
Oh, I forgot to say, another thing that determines stability is going to be ring strain. Right. So let's say we have these rings here. What is the hybridization of all of these carbons here? SP, sp2, or sp3?
They're just sp3.
Uh-huh, that's right. And if it's all sp3, the shape of all of these atoms are going to be tetrahedral. And do you remember the preferred bond angle of tetrahedral um
Was it like
um
120 or
atoms?
something?
Uh-huh. That's trigonoplanar 120. Tetrahedral prefers to be in 109.5.
Oh, okay.
109.5 degrees, where in the cyclopropane, that bond angle is forced to be a 60-degree bond angle. And the cyclobutane, that bond angle is forced to be 90-degree bond angle. And then cyclopentane is like around 107 or 108. And then the cyclohexane is more like 109.5, especially in the chair. But you notice how the six-membered, five-membered ring are more stable because they're closer to the preferred bond angle.
Hmm.
That's why they have less ring strain. And the cyclopropane and cyclobutane, they have more ring strain because the more difference, let's say, let me say, increase difference in bond angle and preferred bond angle means an increase in ring strain, right? And if you have increased ring strain, are you more or less stable?
Um, less stable.
Yeah, less stable. And does that mean more or less energy?
More energy.
Yeah, more energy. That's right. So that's another concept to do this type of problem here.
Okay. Hmm.
Oh wait, actually, let me make this problem a little bit better. Um, okay, let me get rid of these. Let me get rid of these one. This one. This one. Okay. And Okay, yeah, that would be good. Oh, you got it. Nice, nice. Uh-huh. This is the least stable because it has the most ring strain. This is the most stable because it has the least ring strain and it's also trans, which is more stable than the cis. And then everything else is in between, where this one has like still a lot of ring strain, but not as much as the number one, the propane. You got it. That's good. Mhm. Okay. Shoot, my whiteboard is glitching out. Let me do it here. Let's say we have not compared to. Yeah. Which one has lower energy?
This one.
Yeah, uh-huh, that's right. Because that one is more stable due to more conjugation or resonance. Yeah, you got it.
Can you
And then
explain
that means
conjugation again? Like the hyperconjugation again?
oh, that's different from hyperconjugation. Hyperconjugation is different than conjugation.
Oh, okay.
Yeah, yeah, uh-huh. Hyperconjugation is like talking about carbocations, radicals, and alkenes. Like this is a primary carbocation, secondary carbocation, tertiary carbocation. The more substituted the carbocation is, the more stable it is because think of these R groups as donating electrons um like naturally to the carbocation,
Uh-huh.
right? And the more R groups the carbocation has, the more stabilization it has. And this is due to something called hyperconjugation.
Okay, that's what I thought it was, but I just like want to make sure.
Yeah. Uh-huh. That's right, that's right. Conjugation, on the other hand, is something like this, where you are seeing a direct movement of electrons and a direct movement of the carbocation in that case, right?
Okay.
This right here is conjugation. Mhm. In hyperconjugation, nothing is moving directly. It's just like the inductive effect. You could think of it like that. Like the inductive effect is just pushing electrons.
Got it.
But conjugation is like resonance where things are actually moving from place to place directly.
Do you think we'll have to like he'll ask why? I think he said something during like lecture, like you have to explain your reasonings or something every time you draw.
Oh, he said that? I didn't catch that. What the heck?
Yeah. Or like maybe that's just when draw I think maybe that's when like drawing like structures or something like that. I don't know. He said something about like you make sure you have a reasoning. Like he doesn't just want like the answer.
Oh, dang. Yeah, he might ask like why. Like why this was more stable. Mhm.
Okay.
Yeah. Okay. And another thing about hydrogenation is that we know that when we put an alkene through H2 under catalyst like PDC, um, that alkene is gonna gain another set of hydrogens, right? Where let's say that set of hydrogens, let's say these are the pink ones there, and then the new ones are these red ones here, those two red ones, right? Those ones have stereoselectivity. It will go for the less hindered side. So let's say for an example, we have something like this, where we have And he doesn't have to give H2. This works with D2 as well, where D2 is an isotope of H and is called a deuterium ion, right?
Hmm.
Predict the product for this reaction. Like, for example, if you had H2, you could have just drawn the product as this without drawing the hydrogens because hydrogens are already automatically assumed. But if he gives you D2, then you have to explicitly draw out the D.
So the D would go like here, right?
Uh-huh. That's right. That's right.
So it's just basically just replacing the double bond then. Is that what's happening?
Yeah, it's just getting rid of the double bond and adding hydrogens or deuterium ions there. Like we're just adding hydrogens or hydrogen type ions to get rid of the double bond.
Okay.
But in this case, we have to include stereochemistry. Would the D add on the top side or bottom side in this molecule?
Oh. Well, I'm guessing it's the opposite.
Uh-huh. Yeah. That's right, because of something called
uh, I
s-
don't know.
stere
I don't
stereohydrants.
steric hindrance. Okay.
Yeah. Because the top one has a lot of steric hindrance. There's a lot of bulky group blocking the D's attacking that alkene.
Uh,
So it doesn't want to like go on top because there's too much steric hindrance.
oh,
It it wants to go on the bottom because there's more space, less steric hindrance. So that's why they have to be dashes.
that makes sense. Okay.
Like think of a model kit, like the things going towards you. There's too much things blocking it going there.
Right.
Mhm.
Oh, okay. That makes sense. That makes
Yeah.
sense.
There you go.
Okay.
Yeah. Uh-huh.
Well, thank you for your help.
Yeah, no problem.
So you have these office hours every day, correct?
Monday to Thursday, not Friday, Saturday, Sunday.
Okay, okay.
Uh-huh,
I'm
9
gonna
to 10.
I'm gonna try to come to as many as I can.
Yeah. So far, like the first one, just 3 people showed up because they asked lab questions, but then like the other ones, no one showed up at all because like
Really?
yeah.
Oh, okay. Well, I'll probably come tomorrow if I can.
Okay, sounds good.
Appreciate the help. Thank you so
Mhm.
much.
Yeah, no problem, Eva. See ya.
Bye.